Welcome to our quick tutorial. Wait, what am I doing on regression? So as we've practiced, this is our practice with a partner from class. The question is, what would our regression line be given this data? Doesn't matter what necessarily we're predicting, so we don't have kind of a word problem to go along with this one. But X is our predictor and Y is what we're predicting. We're going to use our actual values of Y to calculate our regression line, and then we're going to use our regression line to calculate our predicted values of Y. So the regular Y is our actual values of Y, and the Y with the little hat is our predicted values of Y. So we're going to calculate this regression line, and then we're going to make a prediction for what Y would be if we were to calculate X for 2. So notice X of 2 isn't in this data, so maybe we're interested. What would that be? And so this is a way that we can look at that. Notice that we've also already been given the means of these data, but if not, those are simple to calculate as well. So it's always helpful to kind of go ahead and plot your data points so you can see kind of what kind of relationship this likely is. It looks like there is probably a relationship. It looks like it's a positive relationship, but it also doesn't look super strong. Some of that is also because we have just a few data points, but that is to practice calculating these values. So we were given our X values and our Y values. We're going to first step is to calculate that sum of deviation products. Again, we use sum of products in our shorthand from our book, so SP instead of SDP, but it is the exact same value. So again, we were given mean of X is 3, mean of Y is 2. We're going to use those values to calculate our deviation. So X minus 3, 1 minus 3 is negative 2, 3 minus 3 is 0, 5 minus 3 is 2. We'll square each one of those values. I'm just going across columns left to right. Negative 2 squared is 4, 0 squared is 0, 2 squared is 4. We'll add those together and we'll get an 8. We're going to do the same thing for our Y values. These are actual Y values. So we're going to take our mean of 2. 1 minus 2 is equal to negative 1. 3 minus 2 is equal to 1. 2 minus 2 is equal to 0. We're going to square each of those values. And so we will take negative 1 squared is 1. 1 squared is 1. 0 squared is 0. We'll add those together and we get a sum of squares Y for 2. Now remember, this is different than a correlation when X and Y didn't matter. In a regression, X and Y do matter. So X again is the predictor and Y is what we're predicting. So this is again that same table. To calculate our sum of deviation products, our SP value, we'll take our deviation scores for X and we'll multiply each of them by their deviation score for Y. So negative 2 times negative 1 is equal to 2. 0 times 1 is equal to 0. 2 times 0 is equal to 0. And we'll add those together and we get a sum of deviation products of 2. I went ahead, since we have all of this information, I went ahead and calculated our correlation along the way. Notice that was the exact same process we would have used to calculate our correlation. So we have all of the values that we need to calculate our correlation. So sometimes it can be helpful to go ahead and do that. Remember we talked about our coefficient of determination of how strong that relationship is R squared. So if we've already calculated R, it's really easy to square it and get that value to look at that coefficient of determination. So again, we've got all of these values. Our equation that we're going to do is we're going to start with calculating our regression coefficient, our B value, our slope. Again, we have calculated all that we need for that when we calculated the information that we would use for our correlation. So our sum of deviation products, or SP value, would be 2. We'll divide that by our sums of squared X, which is 8. That gives us 0.25. Remember, this is our slope. So think back to when we plotted lines back in middle school or high school. It was rise over run, right? And so 0.25 in a fraction form would be 1 over 4. So we would rise 1 and we would go over 4. So again, this is that kind of way that we'll be able to plot our information. Let's calculate our A value now. We have our B of 0.25. We have our mean of X. We have our mean of Y. So we'll plug all of that information into our formula. Our mean of Y is 2 minus 0.25 times 3, which gives us 2 minus 0.75, which gives us a regression constant of 1.25. This is our Y-intercept. So we already have everything we need to plot this line. We can also plot this line by calculating values. So we can take our 1.25, put that on our line where it intersects that y-axis, and then we could put another estimated value in for x and get that value. So one of the things you were asked to do for this, we'll put both of those values into our regression equation. So B is 0.25, our y-intercept is 1.25, so our regression line is y is equal to 1.25 plus 0.25 times x. If we want to make a prediction, then using this line, we can put any value we want into x. I asked you to plug in 2 and predict what y would be if x is 2. So we will put that 2 value in that x place, and we will just solve for the predicted value of y. The predicted value of y then is 1.75 because we have 0.25 times 2, which gives us 0.5. We'll add that to 1.25, our regression constant, and we get 1.75. So we can go ahead and plot that value on our line, our 2 and 1.75. We already have our y-intercept of 1.25, and then we can just draw a line between those 2 points. Notice that none of those values, only a couple of those values are really on these kinds of values. So we may not have our dots on the line. These dots had a couple extras. I apologize for that. But we may not have those values on that line. And what we're trying to determine then is how bad or how good of a prediction this is. Think about a line, these linear equations, as a model of how we think this relationship works. And is it a good model or is it not a good model? And the way that we're going to measure that is the standard error of the estimate. So to calculate the standard error of the estimate, you're going to want to predict our y hat values based on the x values that we have. So we have actual y values for each of these x's, but what would our model say? What would our prediction line say? Well, our prediction line for x equals 1 would say we would get a value of 1.5. And our prediction line for x is equal to 3 would be 2. And our prediction line for x is equal to 5 would be 2.5. Now, those are not the same values that we got for our actual y's, right? So our actual y for 1 was 1, and our actual y for 3 was 3, and our actual y for 5 was 2. And so we're going to say, well, how much error is there between 1 and 1.5? Well, it's negative 0.5. And how much error is there between our actual y and this predicted value of y, 3 and 2? Well, that's 1. And how much error is there? How bad is this model or good is this model? We thought the value for 5 would be 2.5, but it was actually 2. So that difference, that error is negative 0.5. We're just going to square each one of those values as we already always have done. Remember, we're doing that because if we just added these values together, we're going to get 0. And we don't want 0 because it doesn't give us any information. But also, the reason it will equal 0 is because our regression equation minimizes this error. And so the fact that it is 0 and our error is good, that means we used our least squared error principle. And we were really able to minimize that error. So we'll add those squared values together and we'll get our error. This is also called our sums of squared residual of 1.5. Again, this formula was left off your formula sheet. I asked you in class to write it on your formula sheet. I really focused on the sum of y minus the predicted value of y squared. That does have a name, and that name is sum squared residual, but let's just we don't have to worry about that as much, and we're going to divide that by n minus 2, which is our degrees of freedom. So we have 1.5. We had 3 scores, so 3 minus 2. 1.5 divided by 1 will give us 1.5. The square root of 1.5 is 1.22. So we don't have a lot of error. This is our precise measurement of how much actual distance is between the regression line and these actual observed information. And so this ends our quick tutorial on regression and measuring the accuracy of that regression line, predicting y values with that standard error of the estimate. Thanks so much. Bye.